All right, the first thing we want to do is find the inverse function of the exponential function f of x is equal to 2 to the power of x. Okay, 2 to the power of x. All right, so let's see if I can make that x even nicer for you. There. All right, cool. All right, so what do we already know about this exponential function? Well, we know a lot. We already graphed it in an earlier video. Let me remind you of what the graph looks like. So we know that this is the curve for the exponential function 2 to the power x. And we know that there's a horizontal asymptote at the x-axis, y equal to 0. So the first thing I would like you to consider is that this function is 1-to-1. It does pass the horizontal line test. So because this function passes the horizontal line test, we know therefore it is 1-to-1. If it's 1-to-1, then its inverse exists. Let me remind you of the steps that we followed in a previous lesson for finding the inverse of a function. All right, here are the steps that we're going to follow for finding the inverse function for 2 to the power x. All right, so let's do it. I'm going to move this screen up a little bit for us, all right? I think that's enough space there. All right, let's find the inverse of this function, all right? So first, I have f of x is equal to 2 to the power x. What I'm going to do is swap my function notation for y. And then I'm going to swap my x and y, or interchange them. Now, here is we have a kind of like a problem here. We want to solve for y. Now, we've solved a lot of different types of equations in our class, but we've never solved an equation where the variable we're trying to isolate is an exponent. So no matter what you try to do to both sides, you will not be successful in isolating y. All right? So allow me to leave this problem for a minute and give you the process for how we're going to solve for y here. Since we don't know what to do algebraically, I want us to consider the solution of this in word form. So in words, y is the exponent. That's what y is. That's what we're trying to solve for. Y is the exponent to which we raise the base 2 in order to get x. Now, in mathematics, this word is here is representative of the equal sign. So we can write this like this. So this is what we have. Y equals the exponent to which we raise the base 2 to get x. So we solved for y in words, right? In words. So obviously, all of these words here would be very cumbersome to continue writing. So we have mathematical notation that would represent these words, the exponent to which we raise the base 2 to get x, and that is the following. Y is equal to log base 2. This expression here, log base 2 of x, represents these words. So log base 2 means the exponent. Y is the exponent. Y is the exponent to which we raise base 2, that's a subscript, in order to get x. Okay, so in using inverse function notation, right, is the last step, our final answer would be written like this. All right, let me scroll up a little bit here for us. Okay, so our final answer would be written like this. Oops. F inverse of x, that's inverse function notation, is equal to log base 2 of x, okay? Y is the exponent to which we raise 2 to get x. All right, very good. So this is the inverse of 2 to the power x. Good job, you guys. I think what would be really great at this point would be to give you the definition, the formal definition for a logarithmic function. So I have a definition. If x and b are positive real numbers, that's really important, positive real numbers with base b not equal to 1. So the base is positive and the base cannot be 1. The base is positive and the base cannot be equal to 1. The logarithmic function with base b is defined as follows. All right, so here it is. Y is equal to log base b of x. Okay, now what's really important is that this is equivalent to, I'm going to put an arrow in both directions. Okay, that's an arrow going in both directions. This is equivalent to b, base b, raised to the power of y will give you x. These two expressions mean the same thing. They're equivalent. All right? They're equivalent. Okay. A little notation for you here. Let's see if I can do this in yellow, back in yellow here. This here is your base. And your base has to be positive, and it cannot be equal to 1. This is called your argument. Okay, your argument. And y is your exponent. So make sure you add that to your notes there, your exponent. Your exponent. Pretty sloppy there, sorry. All right, cool. Now, this here, on this side, I think it's obvious that this side is logarithmic form. This is logarithmic form. This side here is exponential form. This is exponential form. So every logarithmic expression can be, or log equation, can be rewritten in exponential form, and vice versa, right? Which is why this arrow is going both directions. If you have an exponential equation, we can rewrite it as a log equation, okay? All right, our next example has us converting from exponential form to log form, okay? All right, so let me get this for you. The very first one is 3 to the power 4 is 81. This is an expression written in exponential form. You want to write it in log form, okay? So here we go. So when we write this in log form, we do the following. Log. Now, what is, when you look at this expression here, 4 is obviously the exponent, and the base is 3. 4 is the exponent, and your base is 3. And so your base is 3, all right? And a logarithm is an exponent. A logarithm is an exponent. So a logarithm is an exponent, and the exponent is 4. So I set my log equal to 4. And so then the argument happens to be 81. This expression here means the same as this one, all right? So look at this. 3 is the number such that when you raise it to the power of 4, you get 81. 3 raised to the power of 4 gives you 81. Base 3 raised to this exponent gives you 81. Let's try this again. Okay, I have 2 raised to the negative 4th power is 1 over 16. All right, first of all, your logarithm is an exponent, so the exponent is negative 4. Okay, and then we have log base. Now, when you look at your exponential expression, your base is 2. Your base is 2, all right? So then this is base 2, and your argument is 1/16. Okay? All right, remember that when you do this, your base always has to be positive and not equal to 1, and your argument, which is x, must be positive as well. All right? 2 raised to the negative 4th power gives me 1/16. Let's go for another, guys. All right, 9 raised to the power of 1/2 gives me 3. Take a second, maybe pause this video and try to write this in log form. Okay, my exponent is 1/2. 1/2 is the exponent to which I raise 9 to give me 3. How did you do on that one? Did you do okay? I'm sure you did. All right, good job. Let's do one more, shall we? Okay, we have 5 raised to the 0th power gives me 1. All right, the exponent 0, 0 is the exponent to which I raise the base 5 in order to get 1. Good job, everybody. Now the next example has us going the opposite direction. All right, the first one that I'm going to have you consider rewriting is log base 4 of 16 is 2. Log base 4 of 16 is 2. So when you rewrite this in exponential form, the first thing you may want to write is your base. Notice that your base is 4. So that's the first thing I'll write down. Your base is 4. And then the exponent is 2, right? Because a logarithm is an exponent. So 4 raised to the power of 2 gives me 16. There it is. All right? So 4 raised to the power of 2 gives me 16. You know, sometimes I advise my students to draw like a little tail here, and maybe it's a little more clear. 4 raised to the power of 2 gives me 16. So go like in that direction. 4 raised to the power of 2 gives me 16. All right, let's try another one. Okay, guys, log base 2 of 32 is 5. So my base is 2. My exponent, oh, I'm sorry, I guess I'm doing this little tail that I just told you to try, huh? Sorry. So log base 2 of 32 is 5. That means my base is 2 raised to the power of 5 gives me 32. All right, cool. It's pretty straightforward, huh? Let's try another couple examples here. Log base 9 of 27 is 3/2. Can you pause the video and give this one a shot? All right. So if I do my little scorpion tail here or whatever, it'll look like this, right? So then this will be base 9 raised to the power of 3/2 gives me 27. All right, good job, everybody. All right, I want to introduce you to two different types of logarithms. One is a common logarithm. A common logarithm is basically a log whose base is 10. Now, what you have to keep in mind is whenever the base is 10, it's not written. So whenever you do not see a base written at all, then it's assumed to be 10. So it's written like this, log of x, just log of x. Here, the base is not written, so you must understand that the base is 10. The second one is a natural logarithm. A natural logarithm is just a log whose base is e. Remember that irrational number, Euler's number, e. And whenever the base is e, then we use special notation to represent a natural log, and it is ln, okay? ln meaning the natural log of x. ln means the natural log of x. You have to understand whenever they use ln notation, the base of that exponent, the base of that logarithm is e. All right, here we are at example 4. We're going to convert the following logarithmic equations to exponential form, all right? So the first one I have you considering is log of 10,000 is equal to 4. Okay, so log of 10,000 is equal to 4. First of all, I do want you to notice that this is a common log because the base is not written at all. It would be right here as a subscript. And because the base is not shown, we understand that the base is 10, okay? All right, guys, we can do our little tail here if you'd like. 10, the base of 10 raised to the power of 4 gives us 10,000. So then in exponential form, it would be 10 That's the base. Raised to the power of 4 gives us 10,000. Good job. Let me give you another one. Okay, here, notice that this is a natural log because of the notation ln of x, all right, or ln of 1. So here, if I, again, do my little tail, I remember whenever they use ln, they mean base e, so e raised to the 0th power gives me 1, all right? So then in exponential form, it's e raised to the 0th power gives me 1. All right. One more time. Whenever they use ln, you have to understand that the base right here is e. Okay. Very, very good. Let's just do one more. Okay. We have ln of 1 over e is equal to -1. All right. So if you do your little tail again, then you should get that the base is e and the base is being raised to the power of -1, and that is what gives us 1 over e. All right, good job, everybody. Okay, so what we're going to do is we're going to move on, and we're going to go to example number 5. All right, let me give that to you now. Here's example 5. Evaluate the following log expression. Remember the word evaluate means find the value of. So we want to find the value of this expression. Log base 5 of 125. Now, what I really, really want you to remember is that a logarithm is an exponent. Say that with me. A logarithm is an exponent. A logarithm is an exponent. So basically, they're asking you here for the exponent to which you have to raise 5 to get 125. What do you here, I'll write it like this. What do you raise 5 to in order to get 125? Now, they're asking you here for this exponent right there. That the exponent is the answer. All right. So what we know is our perfect cubes. We know that 5, if you raise 5 to the power of 3, you will get 125. So there's your answer. 3 is the exponent. Here, let me see if I can write out the final answer for us like this. Log base 5 of 125 is 3. 3 is the answer. 3 is the exponent to which you raise 5 to get 125. 5 cubed is 125. So the answer is 3. Cool. Let's do another one. All right, so we can do log base 8 of 4. Now this one's interesting. This one is asking you for the exponent to which you would have to raise 8 in order to get 4. Now watch this. If you raised 8 to the power of 1, you would get 8, which is too big because you want 4. If you raise 8 to the power of 0, well, that would be 1, which is too small because you want 4. What I'm trying to convince you of is the following. 8 raised to the 0th power is 1. 8 raised to the 1st power is 8. If you want to get 4, then you should raise your base 8 to a number that's between 0 and 1. Okay, so we know our final answer should be a fraction between 0 and 1 in order to get an output of 4, which is between 1 and 8. All right, cool. Now, I'm going to have you consider solving this question like this. Look at this, folks. This is really interesting. Your unknown is this exponent. Let's give this unknown a variable, okay? Because we always assign a variable to our unknown. So something like, how about 8 raised to the power of x, right? So you and I are looking for that exponent is equal to 4. Now what I would like you to consider is, can you rewrite both the left and the right hand side with a common base? In other words, isn't 8 the same thing as 2 cubed? 2 cubed is the same thing as 8, right? And 4 is the same thing as 2 squared. See, I wrote these, the left and right hand side with base 2. By properties of exponents, we know that this would be the same thing as 2 raised to the power of 3x is equal to 2 squared. So what we can do is we can say, well, if these bases are the same, base 2 and base 2, and these exponential expressions are equal to each other, the only way this statement will be true is if this exponent and this exponent are equivalent. That is to say, in order for this statement to be true, 3x has to be equal to 2. What I did right there is I dropped my bases, my common bases, I dropped them and just set my exponents equal. So when I solve for x here, which is the exponent, divide both sides by 3, you get x is 2/3. Remember what x is? X is that exponent I was looking for. X is the exponent to which you raise 8 to get 4. All right, cool. Then this is my final answer over here. Log base 8 of 4 is 2/3. 2/3 is the exponent to which you raise 8 to get 4. Cool deal. I really want you to pay close attention to this approach, guys, right here in your notes. Notice that this whole approach here was me trying to get a common base on both sides, on both sides. And once you get a common base on both sides, you can set the exponents equal to each other and solve, okay? Hey, by the way, up here, we had said that the exponent to which you raise 8 to get 4 must be a fraction between 0 and 1, and it is. 2/3 is a fraction between 0 and 1. All right, that one was more challenging. Let's see if we can do another one. All right, guys, we got log of 1/100. Okay, 1/100. Notice that this is a common log, right? Did you notice that right away? That the base is not written. The base would be right here as a subscript. It's not written. Therefore, this logarithm is base 10. It's a common log. Okay, everybody, this is really what they're asking you. The base 10 raised to something gives me 1/100. All right? You can do this. 10 raised to something, I'm going to call something x, must be equal to, let's see, 1/100 is the same thing as 10 raised to the negative second power, right? So then you can see then you got a common base, so that must mean that these exponents are equivalent. That is to say, x has to be -2. All right, cool. Then log of 1/100 is -2. -2 is the value of this expression. -2 is the exponent to which you raise 10 to get 1/100. All right, guys, before we move on, I'm going to ask you one more. What about this one? Log of -100. Can you pause the video and give this one a shot, please? All right, how did you do? I'm sure you were thinking of the following. Base 10, right? With the base is not written, so this is a common logarithm. So base 10 raised to some power, that's a question mark right there, raised to some power gives me -100. I hope that you found that nothing works here. I mean, we know that 10 squared is +100. 10 raised to the negative second power just gives you +1/100. Because your base is +10, no matter what you raise +10 to, you will never get -100. This is impossible. This is impossible here. So we say that this evaluation is undefined. Okay? Kind of like saying no solution, okay? This is undefined. Remember that when we defined a log function, we said that this is called your argument. The argument, which was called x in your definition for a log function, we said it had to be positive. I don't know if you remember that. You may want to scroll back or look at your notes. for the definition of a log function, we said this argument had to be positive. So right when you see a negative argument right here, we know, oh, that doesn't make sense. This is undefined. All right, cool. Okay, guys, our last objective for this section is to graph our log functions. So I want you to recall something that we've already done. F of x is equal to 2 to the power x. Okay, 2 to the power x. Now, we've done this function already. We've graphed it already. Let me remind you what we have. Okay, you guys, here's the graph that we did together. We know the domain is all real numbers. We know the range is all positive values. We know that the asymptote is horizontal at y equal to 0, which is the x-axis. And then we know you have these 2 points, the y-intercept of 0, 1, and 1 comma the base, or 1 comma 2, all right? So all of this information you and I derived together in a previous lesson. Now, we know that the inverse of this one-to-one function, the exponential function, will be the log function, right? So let's say g of x is equal to log base 2 of x. I don't want you to lose this, that this is an exponential function here. F is exponential, and g is logarithmic. What is the relationship between these two functions? They are inverses of each other. They are inverses of each other. F and g are inverses of each other, okay? What you can do is go back to example 1 at the very beginning of this lesson to confirm that these are inverses and how we determine that. Now, also, in a previous lesson, when we were studying inverse functions a few videos ago, we defined an inverse function as a one-to-one function such that it consists of ordered pairs of not x comma y, but remember y comma x. Do you remember the ordered pairs switching? And so what we're going to see here is the following happening. All right, so you're going to see that the domain becomes the range for the domain of f becomes the range for g. The range for f becomes the domain for g. So therefore, the domain for g will be all positive numbers. The range for g will become all real numbers. Okay, please take close notes here. Notice that this domain for f, when you talk about its inverse function, it becomes the range. The range for f for its inverse becomes the domain of the inverse, all right? Okay, cool. Now watch this. For the exponential function f, for the exponential function, if your asymptote is horizontal, that means the asymptote for the inverse function will be vertical. Vertical at not y equal to 0, but x equal to 0. Did you see that? So the exponential function had a horizontal asymptote at y equal to 0. Therefore, its inverse function, the log function, will have a vertical asymptote at x equal to 0. So all of this information is swapping, right? Okay, furthermore, for the exponential functions, you had, for the exponential function, you had 0, 1, and 1 comma 2. These coordinates just swap places, right? So then over here for the log function, you're going to have not 0, 1, but 1 comma 0. Not 1 comma 2, but 2 comma 1. Do you see that happening, folks? The coordinates are just swapping when you come over here to its inverse. Let's show the graph. So the graph has to go through 1, 0, and it has to go through 2, 1. Furthermore, the asymptote is vertical, and it's x equal to 0, which is the y-axis. That's the vertical asymptote. So the graph gets infinitely close to that asymptote, but does not cross it. And so the curve looks like this. This is the graph of log base 2 of x. How did we get the graph of log base 2 of x? By taking everything we know about its inverse, 2 to the power x, and basically swapping everything, interchanging everything. The domain for f becomes the range for g. The range for f becomes the domain for g, right? If the asymptote over here is y equal to 0 and it's horizontal, then over here it's x equal to 0 and it's vertical. If these 2 points over here are 0, 1, and 1, 2, then over here they're 1, 0, and 2, 1. I hope you see the relationship between these two inverse functions. We are going to determine the domain and the vertical asymptote for each of the following functions, okay? Here's the first function I want you to consider. F of x is equal to log base 5 of x. Okay, log base 5 of x. Now, we already talked about how the argument, which is x, has to be positive. And we know that by the definition of our log functions. That's what we had said. So far, this is what we have. The domain must be such that the argument must be greater than, strictly greater than 0, has to be positive. Okay, with that being said, the domain can be written in interval notation as 0 to positive infinity. Okay, so there's the domain written in interval notation. Now, as far as the vertical asymptote is concerned, the vertical asymptote will only be changed or altered or moved by a horizontal translation. All right, the vertical asymptote will be shifted or changed by a horizontal translation only. So that is to say, if there is no horizontal translation, then the vertical asymptote stays as it always is at x equal to 0, which is the y-axis. So when you look at this function, notice that there is no horizontal translation. Remember, horizontal translations appear in the argument. They change the argument, and so the argument is just x. Therefore, your vertical asymptote is x equal to 0. All right, the y-axis. All right, cool. Let's look at a brand new function. All right, cool. We have g of x is equal to -3 times log base 2 of x plus 1 plus 4. All right, first things first, let's find its domain. Okay, so for log functions, the entire argument, which in this case is x plus 1, must be positive. Again, that's from the definition for a log function. It must be greater than 0. You can solve for x here. Subtract 1 from both sides to give you that x must be greater than -1. So therefore, in interval notation, the domain would be from -1 to positive infinity. All right. Now, there is a horizontal translation here. There's a horizontal translation right here at x plus 1. That represents your horizontal translation, which is going to change where your vertical asymptote is. Okay. What you can always do, guys, is you can always take your let me write down vertical asymptote for you. You can always take your argument, you could set it equal to 0 and solve, right? And so you can say x plus 1 is equal to 0, solve, and get the equation that defines your asymptote, your vertical asymptote. And there it is. This is your vertical asymptote. It used to be x equal to 0. It used to be x equal to 0, but now it's x equal to -1. Well, because this x plus 1 is a horizontal translation 1 unit to the left. So imagine your vertical asymptote going from x equal to 0 to x equal to -1 by shifting to the left 1 unit. Cool. All right, a brand new function for us. P of x is equal to natural log of x minus 2. First things first, let's find the domain of our function, okay? So by the definition of domain, we know that the argument has to be positive. When you solve this for x by adding 2 to both sides, you get x must be greater than 2. So the domain is from 2 to positive infinity. This is the domain written interval notation. Very good, guys. Now let's go to the vertical asymptote. Okay. Now, the vertical asymptote will be changed if there's a horizontal translation, which there is a horizontal translation. This horizontal translation represents 2 units to the right. So you can imagine x equal to 0, the usual vertical asymptote, x equal to 0 being shifted to the right 2 units. That should give you x equal to 2 as your vertical asymptote. Or if you'd like, you can just take your argument, set it equal to 0, and solve by adding 2 to both sides. And here is your vertical asymptote, x equal to 2. Excellent job. All right, cool, guys. Let's do this brand new example together. Determine the domain and the vertical asymptote for the following function. Okay, so here is the function. It is going to be r of x is equal to 2 times log base 3 of 1 minus x minus 4. All right, cool deal. Let's go for the first things first. Let's talk about domain. Okay? All right, here we go. When we talk about the domain, again, we know that 1 minus x, which is the argument, has to be strictly greater than 0. Now, let's keep in mind here, I'm going to show all my work. When I subtract 1 from both sides, and what I was going to say is keep in mind of the signs, so be careful with signs. So negative x is strictly greater than negative 1. Now, divide both sides by negative 1. Now, remember that whenever you multiply or divide both sides of an inequality by a negative number, the inequality symbol switches. So then this is now x must be strictly less than positive 1. All right, cool. If x has to be less than 1, that means the domain is negative infinity all the way to positive 1, like that. That's the domain for this function. Now, let's talk about its vertical asymptote. Now, as far as its vertical asymptote goes, usually the vertical asymptote is x equal to 0, right? The y-axis. Now, that's going to change here because there is a horizontal translation. Okay, one way you can find the vertical asymptote is to do what we've been doing, taking the entire argument, setting it equal to 0, and solving for x. Okay, I'm going to show all my work here. I'm going to subtract 1 from both sides. Okay, and that will give me, be careful with your signs, negative x is equal to negative 1. And then divide both sides by negative 1. And I get the equation for my vertical asymptote to be x equal to positive 1. All right, cool deal. Okay, guys, this is the last objective for this section, graphing the a log function. All right, so there's going to be a few that I have you graph. The first one I have you graph is f of x is equal to log base 5 of x. Now, from earlier, we know the following two things, all right? So from our work earlier, we know that the domain is all positive values, so it's from 0 to positive infinity. And then we know the vertical asymptote is the y-axis, which is x equal to 0, all right? We know these two things already from earlier. Now, let's get our 2 points, okay? Now, what we're going to do is choose x values. We're trying to work as smart as possible, all right? So notice that if I plug in the number 1 for x, then this would be log base 5 of 1. Now remember, this notation means that base 5 is your, or 5 is your base, and you're going to want to raise 5 to some exponent in order to get 1. What would you have to raise 5 to in order to get 1? 5 raised to the power of 0 gives you 1. 5 raised to the power of 0 gives you 1. So therefore, your ordered pair is, well, don't forget that we let x be 1 and our output was 0. All right, so there's 1 point already that's on our curve. All right, let's get another point. Now, I chose the number 1 already. All right, let's choose, let's say, be smart here is to choose a power of 5. Because your base is 5, it would be good to choose a power of 5. Well, let's choose 5 itself, the first power of 5. So then you would have log base 5 of 5. What does that equal to? Again, that's like saying, what do you raise 5 to in order to get 5? What do you raise 5 to in order to get 5? Well, 5 raised to the first power. 5 raised to the power of 1 gives you 5. 5 raised to the power of 1 gives you 5. Remember the tail that we talked about in the earlier part of this video. 5 raised to the power of 1 is 5. It works for the previous one too. 5 raised to the 0th power gives you 1 for that little tail. All right, cool. So then our ordered pair here is, don't forget, you let x be 5, right? You let x be 5. So then this is 5, comma, 1. Okay, we can take our 2 points that we have, our 2 points, our domain and our vertical asymptote to graph our function. All right, so let's do it now. All right, cool. Okay, so I'm going to say this is 1, 2, 3, 4, and 5 right over there. Say this is 1. All right, cool, guys. Our vertical asymptote is x equal to 0, which is the y-axis. Okay, and then we have these 2 points on our curve now. These 2 points. We have 1, 0, and we have 5, comma 1. And the curve has to get infinitely close to this vertical asymptote. So there's the graph. Pretty cool, no? Again, the process is, let's find the domain, the vertical asymptote, and our 2 points, all right? Cool deal. Basically, I could even zero that down to, or narrow that down to, vertical asymptote and your 2 points. Your vertical asymptote and your 2 points. Let's graph another. Okay, cool. We have g of x is equal to negative 3 times log base 2 of x plus 1 plus 4. Now, we already figured out the domain and the vertical asymptote for this function. From the earlier part of this video, we found that the domain is negative 1 to infinity. You can look back in your notes if you'd like. And the vertical asymptote is x equal to negative 1. Cool. All right, we just need some 2 points. We just need our 2 points, and then we can graph our curve. All right, just like before, let's be smart about what we plug in for x. Now, notice that if we plug in the number 1, 1 plus 1 is 2, and 2 is a power of 2. I'll say that again. 1 plus 1 is 2, and 2 is a power of 2. So let's do that. Let's plug in 1 for x, all right? So g of 1 would be negative 3 times log base 2 of 1 plus 1, then plus 4, which is equal to negative 3 log base 2 of 2 plus 4. Now remember here, this expression, remember a logarithm is an exponent. This is the exponent to which you raise 2 to get 2. What exponent do you raise 2 to get 2? If you raise 2 to the first power, you will get 2. So then all of this here, this log expression, represents the exponent of 1, because 2 raised to the first power gives you 2. So this is going to be negative 3 times 1 plus 4. Okay, and all of this is equal to 1. All right, cool. The ordered pair here is 1, comma 1. That's the ordered pair. Let's generate another ordered pair, all right? How about g of, now again, we want to be smart so that this argument turns out to be a power of 2. You know 4 is a power of 2. 4 is, 2 squared. If I let x be 3, 3 plus 1 would be 4, and 4 is the power of 2. So I'm going to do that. I'm going to let x be 3. That was a little sloppy, sorry. I'm going to let x be 3. So then this would be negative 3 times log of 3 plus 1, and then plus 4. Cool? Let's come down. So then this is equal to negative 3 times log of 4. Oh, I dropped my base. Did you guys see that I accidentally forgot my base here? The base is 2. Let me add that in real quick. Super important, right? All right, of 4 is plus 4. All right, cool. Now, remember this notation is the exponent. A logarithm is an exponent. The exponent to which I raise 2 to get 4. The exponent to which I raise 2 to get 4 is 2. So then this is negative 3 times 2 plus 4. That's negative 6 plus 4, which is negative 2. So then the ordered pair is 3, comma, negative 2. All right, guys, this is really great. I'm going to take our vertical asymptote, which is x equal to negative 1, and the 2 points that we just found to graph our curve. All right, so let's do it now. Okay, let's do something like this. Okay, so how about 1, 2, 3. This will be 3 here. Let's do negative 2 here. This is number 1. Okay, and let's say this is negative 1 here. All right, I'm going to graph my vertical asymptote first. So it's x equal to negative 1, like that. And then the 2 points that you and I found are 1 and 1, 1 comma 1. I think I didn't scale the positive y-axis here. All right, all right, cool. So 1, 1 is right here. And the other point that we found is 3, negative 2. 3, negative 2, like that. All right, so then the graph has to go through these 2 points and infinitely get infinitely close to the vertical asymptote. So then it has no choice but to behave like this, like that, and like that. Remember that this vertical asymptote goes up forever. So you can see that this graph here gets infinitely close to your vertical asymptote, but will not cross it, and it goes down forever this way. All right, cool deal, guys. All right, how about P of x is equal to the natural log of x minus 2. Now, we looked at this function earlier. That is the number 2 there. We looked at this function earlier, and we determined its domain and vertical asymptote already. We determined that the domain is from 2 to positive infinity. The equation that defines its vertical asymptote is x equal to 2. All right, cool. We already found those 2 things out. All right, now, notice that your base is, do you know what your base is? E. Very good, because this is natural log. The base is E. All right? So if we plug in, let's say, the number 3, watch what happens. P of 3 is equal to the natural log of 3 minus 2, which is the natural log, let me rewrite that, the natural log of 1. Now, remember that your base is E. So this is basically E raised to some power gives me 1. All right? So E, remember your tail, E raised to the power of something gives me 1. So the answer is E raised to the 0th power gives you 1. Okay? Like that. So therefore, the ordered pair that you and I just generated is 3, 0. This gives us 3, 0. Can I squeeze that in here? 3, 0 is the ordered pair that you and I just found. Cool. Now let's plug something else in. And we're probably going to need our calculator here, right? So let's see. If we plug in the number 4, a little sloppy, there. If we plug in the number 4, then we have natural log of 4 minus 2, which is the natural log of 2. If you punch that into your calculator, the natural log of 2 is approximately 0.69. 0.69, approximately. Okay, guys, with this information, we can graph our function with this information. All right, let's do it now. Okay, so, oh, I'm sorry, I forgot to write out the ordered pair for us. This ordered pair for that last one was 4, comma, 0.69, okay? Like that. All right, cool. Let's do it. Cool, so let's scale this out a little bit. Okay, so something like that. Let's say this is 4 and this is 2. Let's maybe label every other one. Okay, cool. So the vertical asymptote is x equal to 2, like this. All right. Let me also scale my y-axis here. Let's say that's 1. All right, cool, guys. So one ordered pair is 3, 0. Okay, 3, comma 0. The other one is 4, comma 0.69. So I'm going to eyeball that, maybe about right there. So maybe about right there. So then the graph looks like this. Let's get infinitely close to your vertical asymptote. All right, cool deal, you guys. Let's continue. Okay, I'm going to show you our very last problem, all right? Our very last function that we're going to graph is r of x, which is equal to 2 times log base 3 of 1 minus x, and then minus 4. All right, the cool thing is you and I, just like the other ones, already determined its domain and the vertical asymptote already. All right, cool. We found the domain earlier to be negative infinity to positive 1. The vertical asymptote is x equal to positive 1. All right, cool. Now, notice what would happen if we let x be 0. All right, let x be 0. All right, so we're going to have r of 0, which is 2 times log base 3 of 1 minus 0. I think that's going to be nice for us, minus 4. So then this is going to be 2 times log base 3 of 1 minus 4. Now again, I'm going to help you interpret this notation. Log base 3 of 1 means the exponent to which you raise 3 in order to get 1. The exponent to which you raise 3 in order to get 1. That's 0. 3 raised to the 0th power gives you 1. So then therefore, this is 2 times 0 minus 4. All right? All of, I want to be really, really clear here. All of this right here is basically the exponent of 0. All right? Let's continue. So then this just is negative 4. The ordered pair here is 0, comma, negative 4. Very good, guys. All right, let's get one more point. All right, let's move this up. All right, so let's plug in the number negative 2. Why the number negative 2? Well, if you plug in negative 2 right here, all right, first of all, you're only allowed to plug in numbers that are less than 1, right? Less than 1. So you can't plug in 1. There's a parenthesis here on 1, which means 1 is excluded, because that's where your vertical asymptote is. So the first number that we plugged in that is less than 1 is 0. And so the next whole number would be negative 1. But if you plug in negative 1, it'll be 1 minus negative 1, which will turn out to be 1 plus 1, which is 2. And that's not going to be convenient because your base is 3. Instead, if I plug in negative 2, it'll be 1 minus negative 2. Well, I'll show you right now. And that'll give you 1 plus 2, which is 3. And 3 is a power of 3. Okay, so that's where that thought process is coming from. Okay, so let me plug in, like I said, negative 2. So r of negative 2 would be 2 times log base 3 of 1 minus, watch your signs, negative 2, like that. And then the minus 4. Okay, so be careful with your signs here. This is 2 times log base 3 of, now this is 1 minus negative 2, which is the same thing as 1 plus 2, which is 3. Okay, and then minus 4. Now this notation here means the exponent to which you raise 3 to get 3. See, now I can actually do this without a calculator and I get an exact value. What's the exponent to which you raise 3 to get 3? Oh, that's just the number 1. 1 is the exponent to which you raise 3 to get 3. So then this is 2 times 1 minus 4, which turns out to be negative 2. All right, so then the ordered pair here is negative 2, comma, negative 2. All right, I'll take these two ordered pairs and my vertical asymptote and graph my function. Cool. How fun are we having? All right, so let's do something like this. All right, like that would be, I think, pretty good. All right, so I'm going to say this is 1. And we have, like, maybe this is negative 2, and this is negative 1, okay? And let's scale this out. 1, 2, 3, 4. I'm going to say that this is negative 4 here. I'm going to say this is negative 2 right there, all right? Okay, guys, my vertical asymptote, as we said earlier, our vertical asymptote is x equal to positive 1. The graph has to get infinitely close to that line there, okay? Like that. And then the 2 points that you and I generated right now, one of them is 0, negative 4. Okay, that's a y-intercept. And negative 2, negative 2. So negative 2, negative 2 is about right there, okay? So then our curve has to go through these 2 points like that and get infinitely close to the vertical asymptote. All right, good job, you guys. This concludes this section. I invite you to, as you do in all of the other videos, take really good notes, jot down any questions that you have, bring those questions to me during my Zoom office hours, and watch this video again. I know it's kind of long, but watch little clips of it and watch certain parts that may be confusing. Watch those parts over and over again until it makes sense for you. All right.